Blinded by the light, AR, VR, and vision. I'll be your host today, Robert LiKamWa from Arizona State University. I'm an assistant professor there in the Department of Electrical, Computer, and Energy Engineering and Arts Media Engineering. But tomorrow, I'll be chairing this session where we've got 5 fantastic papers on concepts from vision, augmented reality, and virtual reality as well. So I look forward to hosting these at the session tomorrow. But for today, I was charged to give you a topic preview of mobile computer vision, mobile virtual reality, and mobile augmented reality. So this is the first time that MobiCom's been running these topic session previews. And so they gave us a lot of instructions about what we should be doing, what we shouldn't be doing here. And what we were charged to do is to give you a little bit of an idea. I'm going to read from my emails here. They don't want us to focus on the content of the papers in the relevant MobiCom sessions themselves, but rather give a more general introduction to the area that will prep your audience to understand and appreciate the area when they later listen to the paper talks. So they want us to talk about what are the important advances, which papers opened up new directions, and which papers made significant experimental measurement, verification, or systems building engineering contributions. And so it's actually rather appropriate, I think, when we're talking about these kinds of concepts about computer vision, virtual reality, and augmented reality, because these topics span a whole breadth of different academic areas, including our area of mobile computing, mobile systems, mobile networking, but also going into algorithms and other directions. So I wanted to use this time to kind of talk about where does the mobile computing community fit into this whole picture of these 3 topics here. So we'll take them a little bit at a time, one at a time. You can expect this to take about 45 minutes. So for mobile computer vision, the whole idea is that we've got this bright, rosy future where we've got wearable devices or smartphones or tablets that are looking around the workplace, looking for interesting ways to assist the user, whether that's looking out for important people so you can remember to tell them important things, or looking out for the different people in your lives so it can tell you when you've talked to them recently or when you haven't talked to them recently, or maybe remembering where you placed your keys so you can have a real-world search engine to remember all of these things. And this could be running on a whole host of devices like your wearable Google Glass type of devices, or smartphones, or maybe even these flying little drones that might fly around. But the big problem with all of these is that the battery is going to drain pretty fast when you're trying to run the vision workloads on a tiny little battery. And so on the Google Glass, for example, vision only lasts about 40 minutes when we hook it up and measure it. So why is it such a challenge here, right? We've got other devices like Fitbits that last for days on end. We've got smart watches that last for days. Why is vision so difficult here? And the challenge is that you're dealing with high data bandwidth. And that's creating these high resource needs. Whether that's at the end of sensing or processing the data. Some folks want to transmit the data so you can do the hard work, the heavy lifting offline, off of the device itself. But in any of these, having to deal with all of that pixel data is going to create a huge burden, a huge bottleneck on your system. So the good thing is, in this community, in this mobile systems community, we've been attempting to tackle these problems of high data bandwidth and high resource needs. So one of my papers back in 2013, we were looking at the high cost of energy for sensing from an image sensor. And we're saying, hey, it makes sense that at high resolution, it costs a lot of energy to extract an image. But what if you want a lower resolution image? Right? Maybe we want a lower frame size so we could crop the frame smaller. Or maybe we care about less of a pixel density so we could throw away those pixels and we don't care about them as much. Then shouldn't it be a lower energy cost? Unfortunately, it wasn't the case. So we saw that actually it goes from 320 milliwatts down to 280 milliwatts. So it's still fairly high, even when you're going down to something like 0.1 megapixels. We isolated the cause of that being idle power. When you're sampling fewer pixels, the sensor ends up spending a lot of power still while it's in this idle mode. And so to combat that, we wanted to actually play with the clock frequency of the sensor, and we also changed the duty cycle of when we're actually powering the sensor as well through some standby modes. Could we tune the sound a little bit? It's a little bit hot. Thank you. So what we did was we used some driver management to allow the sensors to actually have more of an energy proportion. And so when instead we went from something like this 280 milliwatts, we brought it down to like 20 milliwatts for the same use case of having 0.1 megapixels and a slower frame rate as well, 3 frames per second, for example. So now we have this nice energy proportional trade-off for our different sensors that we get to use. And so that's really great. But there's more we can do, right? Because maybe we do want those high-resolution images. Maybe we do want these images to come out from these expensive image sensors. So when do we get to decide when we want those images to come out? Well, this work from Saman Nader-Parisi et al., working with Microsoft Research here, is Glimpse. It's a programmable early discard camera architecture for continuous mobile vision. And what these folks did was say, hey, there's some high-power sensing that we want to have happen here. Those image sensors give you valuable information, but we only want to do that at valuable times. And so how do you know when to do that? Well, we'll use cheaper sensors here. Inertial sensors, light sensors, PIR sensors, acoustic sensors, thermal sensors, and even VGA grayscale stereo pairs cascaded together to make decisions about when they actually want to activate further up the stream and eventually activate these high-resolution captures as well. And so they created this cascaded architecture using gating processors to understand when to turn on and off things so that they can go more and more and more resolute in their data capture so that then they can still operate on doing very fancy continuous mobile vision tasks like gesture recognition, like face recognition, while still maintaining a low power budget. So that's a little bit on the sensing side about how they're trying to how the community has been trying to reduce the energy consumption of sensing. But then when it comes to processing, there's another challenge here, that you have to process all of these pixels that are coming out of your sensor. And so there's been a lot of innovation in the industry space of trying to make these things work. And that's been in this OpenCV libraries, for example. That's a computer vision library that's been a tool set of many academics and industry folks to implement these continuous mobile vision tasks, computer vision tasks, in a very efficient way. And so they're tuned to operate very well on processors, whether it's GPUs or CPUs. And then there was an innovation from the Kronos group. Kronos is a consortium, if you will, of multiple different hardware vendors who came together and said, let's create a hardware API for vision. And what that allows the industry to do is allows the industry so that if they all agree to this standard of what their vision libraries their vision hardware needs to provide, then they can be modular and swap out different ways of computing the same kind of computer vision tasks. And so OpenVX Hardware API has been another innovation in that space. And they've been having it implement OpenCV and other higher level libraries as well, so then they can accelerate power efficient vision processing. At the same time, we've seen advances in deep learning, of course, to recognize what's in those images. And Google's been pushing towards mobile nets of recrafting, reshaping these networks so that they run really well on your mobile device as well. So they can run under those power limits, those efficiency limits of running these neural networks on mobile devices. And so Google has been pushing in that direction as well. So these kind of tool sets are very useful to know, I think, especially if you're a PhD student, a burgeoning PhD student in this space. These are things that everybody should know. But they're really just the beginning, right? Because then how do you get these things to run really nicely, really well on your platforms? So to push the frontier here a little bit, there's been a lot of work in creating accelerators for deep neural networks. And a lot of this has come from academia in the architecture domain. For example, Vivian Z's group. And she's got a very nice tutorial and survey of different architectures that run these deep neural networks. A lot of it is, again, looking at the data movement here. The data of the pixels that are going through here, the layers of these filtered data that are going through the different layers of weights. The weights themselves occupy a lot of memory. And so by understanding where all the memory is flowing through, you can create architectures that do this much more efficiently. And so in the architecture space, there's been a lot of innovation here. In the systems side of things, we start to care about how we use these architectures and how we use these libraries, these frameworks that have been built out there. So one of my works from earlier, from 2015, has been about how do we allow these computer vision libraries to operate really well across a multitude of applications simultaneously. So if you're trying to run all those applications that I talked about earlier, you don't want to have to swap between them. You want to have them all running in the background at the same time and all feeding off of the same computer vision features. And so we built this library and service that would allow us to actually intercept any calls into these vision libraries and then cache the function calls into those libraries. And so we have a split process service where if you're trying to do something like, let's say, a face detection, then instead of just doing the face detection on the app itself, it sends the call to a core service that's running on the same device, and it caches, it performs the face detection function and caches the result. So that when a next application is asking for that same face detection, it's going to actually retrieve the result immediately. So it reduces the overhead of each of the subsequent library calls. So I'm going to stand a little bit farther from that speaker because it's still too loud. But that's how we can save on the power consumption of running these additional library calls. So others in the field have also been saying, hey, well, we've been doing a lot of work on offloading in the mobile systems, in the mobile computing communities. So why don't we use all this work towards this goal of having these vision workloads run? And so they've been offloading that. We've been leveraging this work on. They've been leveraging this work on cloudlets. So Kyung Ha et al. At MobiSys 14 proposed this work for wearable cognitive assistance by creating virtual machines on this offloaded cloudlet, so that these tasks can run off of the device instead of on the device. And there's a lot of context inference that goes on to determine which chains to activate or not, with the intent that everything would be extensible so that it could extend to support other functions and scalable for different connectivity problems, performance problems, or reliability problems. So then this could automatically adapt to those sorts of needs. So this is an interesting paper that I feel is a nice paper in the field as well. Moving on from there, there's another paper called Glimpse. Now, if this is feeling like deja vu, already seen, you did see the word glimpse before. That was a different paper on the programmable hardware for early discard. This is a completely different concept here. This is a continuous real-time object recognition framework for mobile devices. And what they're doing here is they're trying to trigger what they should send to that server that they're offloading to and what they should not send to that server. And so the idea here being that we're saying that data is expensive, high data bandwidth causes high resource usage. That's the same with networking as well. You don't want to have to send all your frames over. So what they have done is they've built this client here that does some detection and frame differencing to tell when they want to send different frames over. And if there hasn't been substantial change between frames, then they can reuse the results from the previous computations that have come back from the cloud. And so they're using an active cache to track objects without the server, and they use trigger frames to determine what they want to send to the server or not. And so that's an effective way of creating this kind of object recognition, again, at a low power burden. And so these are some of many works that have been trying to tackle this problem of sensing and processing on visual data while realizing that this high data rate is going to create needs of the system. And so the goal, I think, if we want to look at all of these papers from a 10,000-foot view, it's that we want to reduce the amount of data that we're actually sending, the amount of data that we're sensing. And we want to do that as early as possible towards the sensor. And so for those of you who are new in this space, and for those of you who are students who are working in this space, that's where I think you should focus your attention, is trying to figure out what is the meaningful work to do with a limited budget, and to focus earlier on the stream rather than later. Okay, so that's a little bit about the computer vision side of things. Now, on a completely different topic, we've got virtual reality, right? And completely different because computer vision seems to be about the input into your system, and virtual reality is very much about the output of your system, of what you're seeing when you place your smartphone, for example, inside of one of those Google Cardboards and place it up against your face, right? Or slide it into this Gear VR, put it up against your face. In any of these cases, for virtual reality, you're putting a screen up against your face. So what does the camera have to do with this? Well, not very much. But there's something that links the two together, and that's pixels, right? Now, instead of the pixels being your input pixels for your sensor, they're the pixels that are coming out at you, again, out of that screen near your face. Problem of a screen being near your face is that you need that screen to be very high resolution. That's because, first of all, when something's close to your face, you can actually tell the difference between the different pixels. And if you don't do this properly, you're going to get problems like the screen door effect, where you see the black lines between the pixels, or just really low visual acuity. So you want to be able to provide really high resolution, such as 4K, or even more than that, as device vendors improve. And a lot of that is on the device vendors' side of how do they manufacture better and better screens for this. But where do the mobile systems challenges come in here? It's about how to provide meaningful output to those really high resolution screens. Because again, this resolution is high, and moreover, the user gets to determine the viewport for the content rendering. So you can imagine that there's a sphere of data all around you, and you're looking at a narrow segment of it. So if that narrow segment has to be at a high resolution, then the whole content sphere has to be an even higher size of data that has to come through, a higher data bandwidth that's coming through. And so if you're trying to stream the entire sphere here, you're going to have problems. What people have been proposing have been things like thin client solutions. Thin client, meaning that your client here, your goggles, whether that's your mobile device or some other device, all it's doing is pushing pixels to the screen, and all the heavy lifting is done by some local server. It could be a desktop, for example, in your room. So you send your game state interactions to the desktop sends you your rendered frames back. And that's been fairly effective, except that you're going to have a big problem, and that's these arrows here, especially the arrow coming back. Those rendered frames, as we just said, are going to be high resolution, and especially if you're trying to send more of that content in that sphere, you're going to have problems. And one of the great works, in my opinion, here has been Eduardo Cuervo's, who's been looking at what does it take to create these lifelike virtual reality headsets. And he's saying that, well, if we're trying to do these things with offloading, it's going to be really tough, because we need 6 to 10 times higher pixel density than the current standards are providing, and a 20 to 30 times higher frame rate than the standards are providing as well. And so this is showing you that this is not at all a solved problem by the thin client solution. Right? The thin client solution will get us a little bit of the way there towards kind of the being able to provide this content with less visual acuity, with less responsiveness. But for the ultimate goals, we have a ways to go. And so there needs to be more work in this field to create these kinds of solutions. So one of these works has been Flashback Vr. This is from Kevin Boos and Nin Zhang and Eduardo Cuervo and David Chu at MobiSys 2016. And they're pre-computing and caching the virtual environment on the mobile device itself. So the idea here being that storage is cheap, but computation is really expensive. And so what they're trying to do here is pre-compute all the possible scenes that you would see, and then use those to generate on the fly what your scene should look like. Because, again, storage is cheap, so they can just pull it from the storage. And they've created a way to cache that really, really well, so you can retrieve those scenes effectively as well. And then you can't do that with everything, because that only works with your static content, stuff that doesn't change. So they merge it with the dynamic content in the foreground to actually make things work as well. So that's been a really cool work. A very similar work as well, Furion from MobiCom 17, really cool work here. Again, they're going after this high-quality immersive virtual reality, and they're going after something they call a cooperative rendering. So they've got a remote server that is doing the similar things that Flashback was doing. It's trying to render the objects, and then it's using a mobile client to encode the foreground objects as well. So it's able to integrate these frames together and then create those final frames for presenting to your device. So this is a combination of offloading and this pre-computing as well. There's been other works about looking at how to exploit the network stream more effectively. This one is VAS 360, where they're looking at the spatial and temporal adaptivity in this Infocom paper in 2018. And they're looking at HTTP2, where they've got things like stream termination and stream priority. And they're looking at how do we leverage that to create a really nice 360-degree video player, which is receiving these 360 videos from outside. And so again, you're seeing this trade-off between the visible region and invisible region when they're looking at these spheres of data. So again, this challenge is about filling and controlling the visual field of what you see and providing enough data to fill those screens that are near to your face. So we've got some exciting works at MobiCom this year who are trying to tackle these problems as well. So that's a little bit about mobile virtual reality, and we've talked about mobile computer vision. So you might think that, well, isn't mobile augmented reality just kind of a combination of mobile computer vision and mobile virtual reality? Again, computer vision is kind of the input into your system. Virtual reality is the output of your system to your eyes. So mobile augmented reality would be a combination of the two, right? Where you've got an overlay of the virtual information in front of a physical world and tightly integrated there, so that when you're trying to place a couch that you want to buy from IKEA, you can know exactly where it fits. So that when you're trying to educate students, they can immersively explore the solar system, or immersively explore the human body, or immersively explore some architectural designs. Whole key word here being immersion, that you can actually feel like what it's like to physically operate with these kinds of 3D models. So that's kind of the interesting part where we want to go to. And what's been kind of the game changer here in the past few years, why it's gotten so much excitement, has been accessibility. Right? There's been these AR toolkits from Vuforia, from Apple's AR Kit to Google's AR Core to provide augmented reality libraries. Again, if you're a PhD student in this space, these are the toolkits that you would pick up to start to learn how to operate with these kinds of mechanisms and create some nice AR apps. But there's a problem here, is that when you start to use these different augmented reality toolkits, you're going to find that as good as they are at providing this immersion, this digital physical immersion, there's still a ways to go for operating efficiently with these huge batteries, operating smoothly, so the performance still has a ways to go. If you try to use these, you'll notice that there's still, it can always be improved, the lag, and operating immersively with a higher degree of perceptive ability as well, of understanding what the room is like in terms of, for example, the lighting, and trying to map that properly to the space. So there's still a ways to go for the augmented reality toolkits. And it's really not the toolkit's fault itself. It's that as a community, we can study these problems and look at how the mobile systems community can take on these problems and create more efficient, smooth, and performant devices and systems for these augmented reality tasks. So one of the early works here has been overlay. This work from Puneet Jain et al. And MobiSys 2015, where they're using offloading to assist the AR tagging. So here they're looking at the vision being an expensive process for augmented reality. So they offload it to their network so that they can do some of the feature extraction. They can look up in the database what goes where, and they can place it in the right place, and then it will be able to annotate the augmented reality screen as well. So this is an offloading system to assist augmented reality tagging, and these micro trajectories as well to assist the prediction and other fancy techniques as well. So this is a nice paper in the space. One of the papers that we're working on right now in my lab, this is early work, is to estimate the lighting within a room so that we can map that to our augmented reality objects better. And we're using reflective objects for the moment. So you could have like a reflective ball or a reflective trinket there and observe the reflections off of that object to understand what the light is like in the room, map that to a virtual scene, and create something that's much more immersive. So that's an active work that we are working on right now. And then beyond the ideas of having these augmented reality screens all the time, operating with nice power and performance, there's also another problem that we need to be able to make sure that what we present to the users aren't going to harm them. And so it's very important to secure the augmented reality output as well. So there's been some fantastic work from Franzi Rosner, and this is a Lebec et al. Paper from Oakland 17, which is looking at how malicious or buggy applications can occlude a user's view. So they have some proposed solutions of policies. For example, don't occlude exit signs in a room, because you always want users to be able to find the exit signs. And don't allow the AR objects to occlude each other. And so they have these policies and a policy module to implement them to make sure that applications behave nicely in coordination with each other. So there's a lot of exciting work that's already been done in these spaces of computer vision, augmented reality, virtual reality. But it's just the tip of the iceberg. And then this session, which is on Tuesday, October 30th from 1:20 to 3 p.m., we'll have these 5 papers that are pushing that frontier forward of these 3 spaces. So I hope that I'll see you all there. All right, so this is the topic preview session for Blinded by the Light, AR, VR, and Vision.